This is applied physics course for undergraduate students, and we are discussing chapter 6. I am Dr. Nasir Mirza, and this chapter is about the linear momentum, and its part 2 is about the collisions. So let us start the discussion on collisions. Collisions can be the result of a direct contact where two objects come in contact with each other and collide and transfer momentum. The impulsive forces can vary in time in very complicated manner, and the force can be internal to the system and can be external. And what we do is we observe variations in the active figure, and we see the momentum and how the momentum is conserved. For example, here there are two masses M1 and M2, and the M2 is exerting a force F21 on mass M1. And similarly, the mass M1 is exerting a force F12 on mass 2. Here we see another example in which the collision need not be the physical collision and a physical contact. There are still forces that are applied, and the particles are under the force field. That is, the lines of forces are there, and the particle is passing through in a close vicinity, and then there is impact. And the forces between the particles are really shown through the field lines. This type of collision can also be analyzed in the similar manner as we have the methodology for the physical contact. Now we go further and classify the collision types. There are two types of collisions, the elastic collision and inelastic collision. In an inelastic collision, the kinetic energy is not conserved, although the momentum still is conserved. But in elastic collision, the momentum and the kinetic energy both are conserved. So perfect elastic collision can occur only on a microscopic level. So in microscopic collisions, only approximately elastic collisions can actually be visualized. Generally, some energy is lost to the deformation, to the sound, in converting the system's things. So elastic collision is a approximation. These collisions are described by the isolated system model for both energy and momentum. So there must not be any transformation of the kinetic energy into other types of energy within the system. However, in an inelastic collision, kinetic energy is not conserved, although momentum is conserved, and the object can stick together after the collision. And if this is the case, then it is a perfectly inelastic collision. Let's briefly discuss very important idea, that is the conservation of linear momentum. For isolated system based on two particles with the mass M1 and M2 that are moving with the velocities V1I and V2I at any instant of time, and then afterwards have a collision. For such a model, the two particle interaction model, the conservation of linear momentum is the most important idea. For two particle systems with interaction to each other, the Newton's law, the third law, states that the force exerted by the one particle on another is equal and opposite in direction by the force exerted on particle number 1 due to 2. So particle, the mass M1 is exerting the force F21, and the particle of mass M2 is exerting force F12, then they are equal and opposite in direction. So the conservation says that the total initial momentum, which is equal to the P1I plus P2I, the initial momentum of particle 1 and initial momentum of the particle 2, which is M1V1I plus M2V2I. This is the total initial momentum. And then after the collision, the mass moves with velocity V1 final and V2 final. Then at any time, the momentum is P1 plus P2. So if we take the time derivative, we get the total forces, the net force on the particle 1 and the net force on the particle 2. And this is the total rate of change of momentum. The total rate of change of momentum is the rate of change of momentum of particle 1 and the rate of change of momentum of particle 2. However, no force is acting on the body before the collision. So the dp over dt is equal to 0. So the sum of all forces on particle 1, the net force, is 0. Similarly, net force on particle number 2 is also 0. So after the collision, this rate of change of momentum must remain equal to 0. Therefore, the total momentum remains constant and does not change with the time when net force is 0. So P is constant. Therefore, we can say safely the law of conservation of momentum is saying that total momentum of mass M1 and M2 remains same before and after collision. Collisions do obey the law of conservation of linear momentum when they are isolated collisions, when there are no net forces. The initial momentum is equal to final momentum is equal to constant is the statement of conservation of linear momentum. P1I plus P2I is equal to P1F plus P2F. And in a more description, M1V1I plus M2V2I is equal to M1V1F plus M2V2F. And this is a mathematical statement of conservation of linear momentum, which is saying that the momentum remains constant, the linear momentum remains constant before and after collision. Let us do one example. A glider of mass m1 with a mass m1 equal to 1.225 kg moves with velocity given 3.62 meters per second. It is moving on a frictionless level air track and collides with a second glider of a mass m2 equal to 2.30 kg that is initially at rest. Now, after the collision, the first glider is found to be moving at the speed 1.07 meters per second in the direction opposite to that of the initial direction. So its direction has been reversed and the velocity has decreased. Now, question is, what is the velocity of the mass m2 after the collision? So we will use the momentum conservation in one dimension, and we will choose positive x to be the initial motion of the mass m1. So mass of the first glider is given, velocity of the first glider is given, mass of the second glider is given, mass of velocity of the second glider is equal to 0 initially. So after collision, the velocity of the first glider is given minus 1.07 meters per second, and the velocity of the glider number 2 is not known. So we put the initial momentum calculations and we substitute the values and get the answer. Similarly, the final momentum, here we substitute the M1, V1, but M2 and V2 is unknown for the final, and we say that the conservation law states that the initial momentum is equal to the final momentum. Therefore, writing down this equation, we simplify this, then V 2F is equal to 2.55 meters per second. That's the answer. To get this answer, we have not used the kinematic equations or other form of things. We have used simple conservation of the momentum. Linear momentum remains conserved before and after the collision. Let's do this one more example, and this is really a good description of the conservation law. A man of mass 65 kg is running along a pier. A pier is a platform, basically extended into sea or lake at a speed of 4.9 meters per second. Then he jumps from the pier into a rowboat of a mass 88 kg, which is drifting without any friction on the same direction at a speed of 1.2 meters per second. When the man is seated on the rowboat, what is its final velocity? So we consider only x component of all velocities and momenta. So before he jumps, the man has a momentum p mx equal to m into v for the man. Similarly, for boat, the momentum is p bx, which is for the mass of the boat multiplied by the velocity of the boat vbx. Then total initial momentum is equal to mass of the man multiplied by the velocity of the man along x-axis plus the mass of the boat multiplied by the velocity of the boat along x-axis. And the answer after substitution of the values we get is 424 kg meters per second. This is the momentum, initial momentum. Now, after he jumps and gets seated into the boat and the man move together in the same lake with the same velocity vf. Thus, the final momentum is pf equal to m of man plus m of boat multiplied by the v final. And the law of conservation of momentum says p initial is equal to p final. Therefore, we have already initial momentum 424, and this is the p initial momentum. Then we divide this momentum with the mass m of man and mass of the boat. We get the velocity, final velocity, which is 2.8 meters per second. Now the boat is moving with high speed. The initial speed was 1.2 meters per second, and that was a low speed of the boat. Now it is almost twice or more than twice the velocity because man has jumped and made a part. Again, we say that this kind of the momentum transfer has taken place because of the a jump. Let us briefly talk about the collisions in one dimension, and the elastic collision we know very well between two objects are those collisions where the total kinetic energy as well as the total momentum of the system remains same before and after collision. And in inelastic collision, one is which has the total kinetic energy of the system is not the same before and after collision, even though the momentum of the system is conserved. In these two types of collisions, the momenta of the system is conserved in all collisions, but the kinetic energy need not be. And kinetic energy is not conserved in the elastic collision, in elastic collisions. The total momentum before and after momentum is equal to the total momentum of the composite system. So we can use this and we can write it down in this form: m1v1 plus m2v2 initially and m1v1 final plus m2v2 final. They are same. We can rearrange for the mass 1 and mass 2 and say that the momentum change for the first mass is equal to the momentum change for the second mass, but in opposite direction. The momentum change is also impulse, so we can say that the impulse is equal and opposite on both m1 and m2. J1 is equal to minus times J2. So if we first of all talk about the inelastic collision, the one in which the total kinetic energy of the system is not same before and after collision. Such a collision is shown here for the two masses m1 and m2 with the velocity v1I and v2I, the initial velocities of the both objects, and after the collision, this becomes attached. The mass m1 gets attached to m2, so they are sticking together, and the final mass is m1 plus m2, and it is moving with velocity v final. So the final momentum is m1 v1 f plus m2 v2 f, and the inelastic collision is a collision in which the kinetic energy is not conserved. So the object sticks together, make it an inelastic collision, and they share the same velocity after the collision as vf. Then in perfectly inelastic collision, where the particles are sticking together, the total momentum before the collision is equal to the total momentum after the collision, and we get the reduced form as v1 final equal to v2 final equal to vf. Therefore, the m1 plus m2 is together, and the v final is equal to m1 v1I plus m2 v2I divided by the total mass. Let us consider two particles case for the elastic collision. And in this case, both the momenta and kinetic energy are conserved. So we look into the equations. And for two masses, the initial velocities are v1I and v2I for m1 and m2. After the collision, it is v1f and v2f. Then the linear momentum conservation is the first equation. Look at the equation. It is m1 v1 plus m2 v2 initially, and it is equal to m1 v1 plus m2 v2 finally, and both are same and equal. However, the kinetic energy is also conserved, and in this case, m1 v1 I square plus m2 v2 I square is equal to m1 v1 f square plus m2 v2 f square. And typically, two unknown are employed to solve such equation. So we need two equations. What actually is demanded is to find out the final velocities after the collision. If the initial velocities and initial masses are known, then final velocities must be sought. So if we consider the velocities along the horizontal direction and we simplify them, the equations, and we try to solve the equations. The first equation is the momentum equation, the conservation of momentum. The second equation is the kinetic energy conservation. And in a little bit manipulation, it will result as V1 I minus V2 I equal to minus times V1 F minus V2 F. And the relative velocities of the two particles before collision equal to the negative of their relative velocities after the collision. And suppose that the masses and the initial velocities of the both particles are known, then from those two equations, we can have the V1 final and V2 final in this form. We need not memorize this, but we need to understand these two equations. So let's apply special cases. The first special case is if the masses are equal, m1 is equal to m2. Then above equations will reduce. Look at the first equation. m1 is equal to m2. Then this term is 0. m1 is equal to m2. And if m1 is equal to m2, then this will become 2 times m2. So 2 times m2 will cancel with each other, and we will get v2I. So v1f will become v1f will become v2I. Similarly, v2f will become v1I. Look at this. This is the final velocity of the first particle. It is the initial velocity of the second particle. And the final velocity of the second particle will become the initial velocity of the particle number one. So particles exchange velocities. When the masses are equal, after the collision, particle will exchange velocities. Particles do exchange velocities if their masses are equal. This is a special case for the elastic collision of two bodies. Next is when the target particle is at rest. So another special case is when particle M2 is initially at rest. Then V2I is 0. If V2I is 0, then this term is gone, and we are reducing this V1F equal to M1 minus M2 divided by M1 plus M2 times V1I. Similarly, V2F is equal to 2M1 divided by M1 plus M2 times V1I. So both are now depending upon the initial velocity of the first particle. Further simplification can happen. And let me show here. Now, if the mass M1 is equal to M2, then this V1F will become 0. And V2F will become V1I, which shows that if the initial particle was at rest, the particle number 2 was at rest, then the final velocity of the particle 1 will be 0. And the final velocity of the particle number 2 will be exactly the initial velocity of the particle. So if one particle is at rest and their mass is, the colliding particle's mass is equal, then the colliding particle will be replacing the place of the particle number 2, and the particle number 2 will be moving with the velocity of the particle 1. Here we see another very good example of a massive target. If the mass M2 is very, very large as compared to the mass M1, then we have these simplifications. V1F is equal to minus V1I plus 2 times V2I, and the final velocity of the particle number 2 is the initial velocity of the particle. So if the massive particle is moving slowly or at rest, then we say that the lighter particle will have the velocity minus times the initial velocity. So lighter particle will collide and will bounce back with the same velocity with which it came. And the final velocity of the particle number 2 will not change, it will remain same. So massive particle will keep on moving with the same velocity, and the lighter particle will collide with massive particle, which is nearly at rest, and will move back, will be reversing its direction or rebounding, so as to say, and will move exactly with the same velocity in the opposite direction, which was the initial velocity of this particle. Massive particle will remain in the same state. Then case number 4 is a projectile motion in which we have the M1 very, very large as compared to M2, where massive projectile is coming and hitting a small particle. So if this is the case, then the final velocity of the particle 1, which is very large particle, will remain the initial velocity of the particle 1. And the final velocity of the particle 2 will be obeying this equation. If the light particle is initially at rest, then you see the final velocity of the particle 1 will be the initial velocity of the particle 1, and the final velocity of particle number 2, the smaller particle, will become twice the initial velocity of the particle 1. So the motion of the heavier particle is nearly unaffected with the much lighter particle, and if the lighter target particle is initially at rest, it will start moving after the collision at the twice speed of the initial mass. So in alpha particle scattering, the incident alpha particles, they were very massive particles, and as compared to the electrons. So they were initially unaffected by the collisions by the electrons. And alpha particle will be deflected only in rare encounters with the massive nucleus of the target particles. Let us do a example. We have already seen it, but in modern physics. But we will do it from the other point of view, that is the change in the momentum. A alpha particle, a nucleus of atom of helium, we say M1 mass is equal to 4 atomic mass unit, is accelerated to a velocity of 1.52 into 10 to the power 7 meters per second and collides head on with an oxygen nucleus. When the mass of the nucleus is equal to 16 units, it is M2. So it is 16 atomic mass units. And uh, after the collision, oxygen nucleus moves with the velocity of 6.08 into 10 to the power 6 meters per second. It is along the original direction of motion of the alpha particle. The question is, what is the velocity of alpha particle after the collision? Again, we know very well in such problems of collisions, we will use the initial momentum and the final momentum, and we will say that the initial momentum is equal to total initial momentum is equal to the total final momentum. So conservation of momentum is allowing us to find the velocity of alpha particles. We take positive x direction to be that of the initial velocity of alpha particles, and we will let particle 1 to be the alpha particle, and we will let particle number 2 to be the oxygen. So we'll write the oxygen, the velocity initial is roughly 0, and substituting this, the m1 v1I plus m2 v2I equal to m1 v1f plus m2 v2f. And here we have 4 multiplied by the velocity plus 16 times the velocity, which is 0, plus 4 times the velocity of the final velocity of the particle 1, which we don't know, and 16 times the velocity of oxygen, which we know, and we find the velocity of the alpha particle as 9.12 into 10 to the power 6 meters per second with minus sign. So it is in the reverse direction, opposite to the x direction, and its value is calculated. So such a complicated and complex problem can be reduced to a very simple solution, and the methodology of solution is very simple if we believe that we know conservation of the momentum, which will allow us to find the velocities of unknown quantities. Thank you so much. We stop here with this lecture, and we will carry our discussion on the applied physics topics in coming lectures. Thank you so much.